Nice meeting you all. This is Wenhu Chen from University of Waterloo. I'm also a Vector faculty member. So today it's our pleasure to have Professor Kuldeep as Meel with us today for the Vector faculty affiliate talk. Kuldeep is an associate professor of computer science in the Department of Computer Science at U of T. His research interests lie at the intersection of formal methods and artificial intelligence. He's a recipient of the 2022 ACP Early Career Research Award, the 2019 NRF Fellowship for AI, and was named the AI's 10 to watch by IEEE Intelligence Systems in 2020. His research program's recent recognition includes the 2023 CACM Research Highlight Award, CAV 2023 Distinguished Paper Award, 2022 ACM SIGMOD Research Highlight, EJCI 2022 Early Career Spotlight, Best Paper Award nomination at ICCAD 2021, and DATE 2023, first place in model counting competition in 2020 and 2022. He's passionate about teaching and most proud of being a recipient of the university level annual teaching excellence awards in 2022 and 2023. I believe it's from NUS, right?
Yeah.
And now I will give the stage to Dr. Kuldeep to start his talk.
Thank you. Thanks a lot, Venu, for the introduction. Good morning, everyone. So I want to talk about a topic that's perhaps will be a little far away from the normal comfort zone for some of you. So please ask questions as we go along. I'm going to situate the talk about a topic that is of crucial importance in the field of design automation. And that's where you can see the papers have appeared. ICCAD date, these are the design automation conferences. The work I'm going to talk about has been led by my former PhD student, Priyanka Golia, who is a tenured faculty member now at CISPA, and in collaboration with Subhajit Roy, who was Priyanka's PhD co-advisor, and Frederick Silvosky from TUVM. So with that as the backdrop, let me get started with the importance and context of the problem. So we are going to talk about what's often called the holy grail of programming, which is to synthesize a system. In particular, the user should be able to just state the specification, and we want the underlying computer or the system to be able to synthesize a system that will satisfy this specification. The particular class of specifications we want to talk about are relational specifications. So there are a set of inputs and outputs, and then there's a relational specification often written in constraints to capture the the specification between input and output. The systems one cares about are often either low-level programs or the circuits. So here you want a physical circuit to be designed. And much more broadly, what all of this reduces to is finding functions for each of the output variables in terms of the input variables. So let me state the problem very formally. So what we are given a formula over two sets of variables, x and y. So this is a Boolean formula. We are going to focus the entire problem in the context of finite domain variables, which means that we can just focus on the Boolean setting, which is also what people care about in practice. So we have a Boolean formula over input and outputs, and we want to synthesize a set of function vector, a vector of functions, f1 to fm, such that what does it mean for these to satisfy the specification? It means that if you look at the formula on the left side, it says that for any value of y, if there exists a y so that the specification could be true, then it would be the case that if you were to substitute y with this vector of functions, the specification would be true. More logically what it says is for all x, if there exists a y so that one can satisfy the specification, then it should be the case that if you were to substitute y with f of x, it would still satisfy the specification. Each of these functions are called column functions. This is a problem that has been studied for now nearly 150 years. Skolem proved the decidability of this problem in the general first order logic in early 20th century. So hence the name Skolem function. And these vector functions are called Skolem function vector. Just to give an idea about the scale of the problem, the number of input variables are often in the range of 2,000 to 10,000. So you can see the possible space is very large because that would be 2 to the 10,000. So this is a very large space. And again, the number of outputs we care are about between 1,000 to 5,000. I think let me give a quick example to concretize all of this. So here, let's say we had two input variables, x1 and x2, and one output variable, y1. So we can write a specification that looks of the form x1 or x2 or y1. What can be a possible column function for y1? Well, let me suggest that one possible column function is not of x1 or x2. Is this correct? Well, we are going to check. We know what it means to be a column function. It should mean that for every assignment of x1 and x2, we are going to check whether there exists an assignment to y1. In this case, it turns out that for every assignment of x1 and x2, if we were to assign y1 to true, then phi of xy would evaluate to true. Let's see what happens if we substitute y1 with the function that we have. We get a formula of the following form, x1 or x2 or not of x1 or x2. And this formula, if you simplify, is just trivially true. So it is indeed the case that for all assignments of x, if there exists a y, which in this case, y equals to 1 always exists, and that would satisfy the specification, then also substituting y with f of x satisfies the specification. Yes, if you have any questions, please unmute yourself and ask it. There can be many other possible column functions. And in fact, that's kind of what makes this problem much more hard to solve it in practice. For example, there can be a column function not x1. This column function not x2 is correct. Even a constant column function is correct in this setting. So for all values of x1 and x2, you could have just said that I want y1 to be 1, which indeed is the case that works out. So there can be many possible functions. And this is where the setting is very different from traditional machine learning settings, where if you were to think in the form of machine learning, then you have the x as a set of possible features. So for different assignment to the feature, there are many possible assignments to the labels, and all of them are equally acceptable. So there is no preference over one over the other. Of course, as we go along searching for functions, we would prefer to get smaller functions because that are easier to find. But any of this column, we want the tool to just find one possible column function, and it can find any of these column functions. And there exist many column functions for a given specification. And the reason there exist many column functions is because phi is a relation. It means that for every assignment to x, there can be many assignments to y that satisfy phi. So I would wait here for some questions because I know this is not very general setting if you are not familiar with logic. Yeah.
Hey, Kuldeep, can I ask a question real quick?
Yes.
Can you explain again the difference between classical machine learning? Maybe the way that I understood it is that the aim for finding f is different here.
Yeah, so the
But
biggest difference comes because for every assignment of X, there can be many possible assignments over Y. So the underlying specification is a relation, not a function. So there is, for every assignment of X, there is not one particular assignment over Y. So if you think from the perspective of, for every assignment of feature, there can be many possible labels, and all of them are equally good.
so is it correct to say that in classic supervised machine learning, we have covariates and we have labels that are both fixed, but in this case, at least the Y is not fixed. And
yeah, there can be many possible assignments of Y here. Yeah.
And so what is the goal that we're trying to find here? Are we still trying to learn the mapping from X to an infinite possibility of Ys?
Well, we want to find only one possible mapping here. So think about, let's consider this setting that we have here. You see, for when x1 and x2 are 0, 1, y1 can be both 0 or 1. But we just care about one possible mapping that we should be able to find. So if you look at the function that, one possible function here is not of x1 or x2. The function that we find will, of course, for every assignment of X, will give a unique assignment over Y. But the underlying relation can have many possible assignments.
Right. So is it correct to say that although Y isn't fixed, the characteristic formula of the theta of X and Y should together satisfy some property? That's why we could have possibly infinitely many Ys, but it's not completely unbounded. It still needs to collectively with the X satisfy something.
Yes, that's precisely. I mean, we are considering the finite domain setting, so there are not infinitely many, but there can be exponentially many such assignments. But this is precisely what it means, that for every assignment over X, if there is an assignment to Y so that the constraint could be satisfied, then it would be the case that if I were to substitute the function that I found, it would also be able to satisfy the specification.
Interesting. And sorry, I think just a quick follow-up to this. Did you say that if there exists a Y that satisfies the characteristic formula here, then there must always exist an F that maps, or no? We don't know that.
So that turns out to be the case even for infinite domain, and that was Skolom's breakthrough result in 1910. So this is considered one of the biggest breakthroughs in logic in early 20th century. So it's not immediately clear why it should be the case for first order logic, where there should be a function that you could decide on. But of course, in the finite domain, it is the case that there will always exist a function.
Okay, thank you.
Yeah. Okay, so I hope if you have some more questions, please do ask at this point, because the rest of the talk is about this problem. All right, well, now you have signed up for the rest of the talk. So why do we care about this problem? Well, it turns out, this is what's called quantifier elimination. If you have a quantifier exists or for all. To eliminate the quantifier, which is at the core of the symbolic reasoning, you find these functions which are called Skolem functions. So if you go back, remember now the formula exists y phi of xy is equivalent to the formula on the right side, and there is no quantifier here. So at the core of symbolic reasoning is quantifier elimination, because once you eliminate all the quantifiers, we have lots of ideas on how to solve system of equations. So this is at the core of symbolic reasoning. This has been also studied in a lot of other settings. For example, you are given in design automation, one is trying to design a circuit, or often you have a large component and there are some parts that you want to automatically design, and that's where the circuit synthesis or functional synthesis comes in. And you can show similar settings for program synthesis and so on. So this is a very well-studied problem. It has been, the study was initiated in Boole's book on laws of thought. Then there's a lot of work in the 20th century. And since computer science began, there has been a lot of work in different areas of computer science. So if there has been a lot of work, it turns out there are lots of attempts to solve this problem. And there are very different ways of trying to solve this problem. I'm just giving a snapshot of some of the work over the last 15 years or so. So there's a line of work that goes on what's called the proof of validity. You look at this formula, you try to prove that the formula is valid, and from the proof, we can extract such functions. This line of work, which is coming from the classical AI side of knowledge representation, so where you ask that in what form you can represent this specification so that extracting such functions is easy. There's another line of work that builds on in the progress of set solving and tries to lift the constraint solving ideas to function. Constraint solving is about finding assignment to variables, and you can lift it to find assignments to functions, and so on. When we started looking into this problem about 3 years ago, we found that scalability still remained a major challenge. I mean, this is an NP-hard problem. We know that unless under standard complexity conjecture, there are even specifications for which there will exist exponentially large functions. So this is a really hard problem. We don't expect it to solve for every setting, but we want to push the envelope of scalability as further as possible. Maybe one quick comment I want to make here, that you can think of factorization, which is a very fundamental problem in cryptography, as instantiation of functional synthesis, because factorization is just writing x equals to y1 times y2, and y1 and y2 both should not be 1. So finding prime factors is same as functional synthesis. Okay, so I want to discuss an approach that we have been building for past few years. This is an approach that sits at the intersection of relying on the advances in data-driven methods. In order to generate the data, we rely on advances in constraint sampling. So this is to generate samples out of set of constraints. And finally, we combine it with advances in formal methods. And the approach that we have is called Manthan. So here's how the high-level view of the approach works. We start with a specification and we generate the data. In order to generate the data, we rely on constraint samplers. So these are samplers that can take a set of constraints and output assignments to x and y that satisfy this set of constraints. Once we have the data, we rely on off-the-shelf, very simple techniques here of decision trees to learn candidate functions. Of course, it will turn out that these candidate functions are not fully correct. What do I mean by not fully correct? Not for every x, they give the right assignment to y. So we had to go through a loop of verifying whether they are indeed correct column functions. And if they are not correct, then we go on to repair them. And we go through this verify repair loop until we finally are able to conclude that here is the function that is indeed correct column function. So let me give a quick peek into how each of the steps works. So first, we are going to start with the specification and we are going to generate the data. Once we have this data, we can now view this as a problem where we have the set of features and the labels. So we are going to learn the decision trees out of it. Once we learn each of the decision trees, from the decision trees, we'll extract the functions. Once we have these functions, we want to check if these functions are correct or not. For that, we are going to come up with another formula. I'm going to go into more details about it. So this is, we call it the error formula. This formula has a special property. If this formula is unsatisfiable, what it means is there's no assignment that can satisfy this formula, then we can certify that the function we have obtained are correct column functions. If this formula is satisfiable, then we get a counterexample. So we go on to repair the counterexample, and we keep doing this until we are finally able to have the error formula being unsatisfied. Okay, so this is how the overall approach is. We first generate the data, then we learn the candidate functions, and then we go through this verify repair loop until we are able to come up with functions that are indeed correct. Any questions at this point? Yes, Sheila.
Hi, Kuldeep. Sorry, I came in a little bit late, so this may be something that you've already addressed. Can you describe the nature of the functions and the nature of the functions, the nature of the repair, and any syntactic restrictions on the input formula? I assume the formula is just a Boolean formula, not linear temporal logic or anything more sophisticated.
Yeah, so here we are dealing with just the Boolean formula, and from the perspective of the column function synthesis, we are okay with any function. Of course, as it turns out that we are more likely to find the functions with more compact representation, but from the problem formulation, any of the possible functions are correct.
But yeah, and it's not, there's no assumption of noise in the input. I know because the input function is precise, one would assume that the function that approximates it is, or that characterizes it is also precise. There's no uncertainty in it, even though you're using machine learning techniques to learn that function.
Yes, absolutely. And I think that is kind of that brings me to the remark that I wanted to make here, is that in this setting, we really care about finding functions that are correct. It means that for every assignment of X, they should be able to give correct assignment over Y. There shouldn't be any error.
Perfect. Thank you.
Okay, so let's get into each of the three components. So the first component is to generate the data. And at this point, the question is, how do you generate the data? So we have these formulas. Just a quick comment, given a Boolean formula, even finding one satisfying assignment is NP complete problem. So of course, this is a hard problem, but we have access to samplers. What are the samplers? They can sample satisfying assignments of a formula. So first step would be that maybe we should just randomly sample satisfying assignments of the formula. But this is where the fact that phi is a relation, not a function, plays a crucial role. In particular, remember, for every assignment of X, there can be many possible values of Y. And why does that matter to us? Well, let's see it with an example. So I have written down a specification, which is really what we saw earlier, X1 or X2 or Y1, and another just similar function over X1, X2, and Y2. So here is what the truth table of phi looks like. So for assignments of X, when X1 and X2 are 0, 0, Y1 must be 1. I hope you are able to see that when both are 0, then Y1 must be 1. But Y2 can be 0 or 1. Similarly, when X1 and X2 are 1, 1, Y2 must be 0, but Y1 can be either 0 or 1. So if we were to rely on a uniform sampler, then a uniform sampler, anytime it has choices between 0 and 1, it's going to arbitrarily pick one of, it's going to pick with equal probability 0 or 1. So we might end up with a truth table like this. Of course, this is a small formula, so we can afford to generate all 4 possible assignments over X. We are going to deal with the cases where the number of X are of the order of 10,000. So of course, we cannot generate 2 to the 10,000 rows. But let's just focus on this case for now. So if we were to generate a table like this, and let's say we rely on any powerful learning method, we'll be able to learn the functions. For y1, that turns out to be not of x1 or x2, and for y2, it turns out to be not of x1 and x2. These are just the functions looking at the table here. This is all fine. I mean, these are correct column functions. But if you remember, there could have been even simpler functions out there. It would have been okay to have a function not x1, or perhaps just not x2, or even a constant function would have sufficed. So why do we care about that? Well, if the number of x are very large, and the initial data that we generate corresponds to more complicated function, then we need way more samples in order to be able to learn such functions. So it would be advantageous if we could generate the data that could allow us to learn simpler functions. So it would be great if we had access to some magical sampler that could figure out that whenever for y1, it can take value both 0 or 1, it should take value 1. And in case of y2, whenever it could take value both 0 or 1, it should take value 0. But there are no syntactic restrictions on the formula, and it's hard to deduce such information just by looking at the syntax of the formula. Just to, if you haven't looked at this formula, these are gigantic formulas over thousands of variables. So these go over, tens of thousands of lines. So you can't just look at the formula and guess the nature of what y1 and y2 should do. So we don't have access to a magical sampler. So what we can do? Well, one thing that is clear is that we shouldn't rely on uniform sampling. So perhaps we should do sampling that is biased. And in this case, we rely on weighted sampling. So what is weighted sampling? It assigns weights to all the variables between 0 and 1. And now weight of an assignment is product of the weight of the variables whose value is set to 1 times 1 minus the weight of the variables whose value is 0. So if we assign weight of 0.5 to x1 and x2 and 0.9 to y1 and 0.1 to y2, then look at an assignment here, which is to say that x1 is 1, x2 is 0, y1 is 0, and y2 is 1. Then the weight of this assignment is product of the weight of the literals, and this is what it corresponds to. So uniform sampling is a very special case where all the variables get assigned equal weight of 0.5. So the important question here is that how do we come up with the weight functions? I don't mean to claim that we have the final answer on it. I'll tell you the heuristic that we developed, which seems to work well in practice, and I hope some of you will get interested to explore further. So here is what we did. We want to figure out whether the variables are biased towards 0 or 1. So initially, we generate samples by setting the weight of yi's to 0.9, which would mean that they are much more likely to be generated with value close to 1. Then we also generate a set of samples with their weight biased towards 0.1. And then based on the samples that we have, we do some statistic computation on the solutions we are seeing, and we compute weights for each of the yi variables. And then we generate rest of the samples with these weights. Constraint sampling itself is NP-hard, so we can generate about 5 to 10,000 samples. So again, we are in the regime where we are not able to generate too many samples, even though the number of pieces themselves are of order of 10,000 variables. How do we generate samples? There has been a lot of work that has happened in the past decade. So we rely on the advances that has happened in the design of these samplers, and we are able to rely on the state-of-art samplers for this. So that concludes the first component. So we start with the formula. It turns out uniform sampling is doesn't work very well, so we had to rely on weighted sampling, and we have some heuristics to determine weights for each of the variables, and that's how we generate the data. Any questions?
I have a question.
Yes.
So Kuldeep, I'm wondering if you've tried relaxing this. So it's somewhat easy to sample from or to generate a feasible solution, let's say from a linear program. So I'm wondering if you've thought about essentially putting all these constraints, relaxing them into a linear program, and then just putting a cost function of, let's say, 1 to the linear program to generate a feasible solution. Would the relaxation essentially be useful here?
So that was indeed one of the approaches for generating samples. It turns out that the kind of formula that we care about, the solution space is very, very sparse. And in that case, such relaxations don't work well at all. So usually you get something in the relaxed space, but you are not able to extract any assignment over the original set of variables.
Good.
And I will also show some experiment for different samplers, and one of the sampler relies on this relaxation idea, and we'll see that it struggles. Okay, so now let's get to the second part. So second part is kind of what we wanted to do was really rely on off-the-shelf techniques here. So we are relying on decision tree classifier. So the scikit library in Python. So what we have right now, remember we have generated the samples. So we have a set of features and the labels corresponding to those. And now we just want to learn functions for the variables in terms of the rest of the variables. So what we can do is we can learn function for y2 in terms of x1, x2, and y1. And then we can learn function for y1 in terms of x1 and x2. You might have made the observation that learning a function for y2 in terms of x1, x2, and y1 is okay because y1 itself is a function of x1, x2. So how do we learn each of these functions? Well, we are now going to treat these as the set of the features and this as the label. We give it to the scikit, it generates the decision trees for us. Once we get these decision trees, how do we extract the function out of it? You can just look at the path that goes to leaf 1. So in particular, what we get here is if not of x1 and not of x2, then the value should be 1. Or if x1 and not x2, then the value should be 1. Otherwise, the value is 0. There is something worth remarking here that this corresponds to one level decision list. So what do I mean by a level of decision list? The P1 and P2 can be reordered without any effect on the function. So there's only one inherent level of the decision list. So if you were to look at this representation, we can reorder P1, P2 as we want. So one question here is that, well, when we are learning from scikit, should we allow errors or not? What I mean by errors, should we have any training error here or not? And this is where, in contrast to a lot of learning settings, remember there is no noise in the samples we generated. All of them are indeed satisfying assignments of the formula. But at the same time, the data we have generated is only a subset of the possible solutions. So perhaps we should allow errors. And it turns out that allowing errors turned out to be the right approach. From the formal method setting, this is a bit surprising because a lot of effort in formal methods is on abstractions. And this is where we are relying on approximation. So in case of abstractions, you start with an over or under abstraction, and you slowly refine. Okay, so that concludes the second part. So we have generated the data. We learn each of the candidate functions. The number of I variables are 2 to 5,000 variables. So we learn about 5,000 decision trees. And now we have to see if the functions we have learned are correct or not. Yes, Sheila.
Hi, I'm curious whether you spent any time thinking about which output variable was going to be the one that you used to express the function, because I can imagine that selection of that variable, especially when you imagine that there are lots of output variables, is really going to affect the fidelity of the function that you can learn.
Yes, that's a very excellent observation. So in particular, we shouldn't go by syntactic naming of the variables. So what the way we actually do is we pick the first. You can pick any of the first variables. Then you see that, let's say we pick y100, and we see that the function for y100 depends on y1. So when we are picking y1, we should make sure that we don't put y100 in the set of features. So we slowly build a partial dependence of the variables. And it turns out that's very, very crucial. So if you were to, this order that is coming in from some statistical information underlying data is very crucial. So you don't want to fix an order a priori. In fact, fixing the order just completely messes up totally. Okay, so now let's get to the third part, which is that how do we know these functions are correct? Well, first, from machine learning setting, we learned these functions and we could just do some training tests. We can try to compute some test error. It turns out that what we learn has some accuracy somewhere close to 80% or so, which is not at all acceptable in our setting. In fact, 99.99% accuracy is also not acceptable, because 0.001 times 2 to the 2000 is a very large number. So we want it to be fully accurate. For that, we have to come up with some way of checking if these functions are correct or not. And this is where we rely on a very beautiful observation about 7 years ago by John and co-authors. So here's the observation. We can come up with another formula, and we'll call it as an error formula. And this formula looks of the following form. It is phi of xy and negation of phi of xy prime, where y prime are set equal to f. So what is this formula asking? It's asking, is there an assignment of x and y so that the relation, the specification is satisfied? But if you were to substitute the output of these functions, then the specification would be falsified. So is there an assignment that could satisfy the specification, but if you were to substitute the output of the functions, it would falsify the specification? So if there is no such assignment, then we know the function we have is correct, because for every assignment over x, if there is a way to satisfy phi, then the output of the function also satisfies phi. So when this formula is unsatisfiable, it's a good news. And if this formula is satisfiable, then we have a counterexample, and we can use that counterexample to repair. Again, this itself is a SAT call, but we are in the world where the SAT solvers are incredibly powerful. This is one of the biggest, one of major advances that has happened in symbolic reasoning. We have access to these really powerful SAT solvers, so we can give these kind of formulas to the SAT solvers, and they can work incredibly fast. So now we have a counterexample to fix. So how should we go about doing repair with respect to this counterexample? So let's say this is the counterexample which assigns values of 1 to x1 and x2, and tells us that for when x1 and x2 are 1, 1, then we could assign y1 and y2 to be 1, and we would be able to satisfy the specification. And our current candidate function give assignment of 0 and 0 to y1 and y2. So what are all the functions we should be trying to repair? So first, it looks like we should be repairing all the cases where yi and yi prime don't agree. But it turns out, remember, phi is a relation, not a function. So it could be the case that when x1 and x2 are 1, 1, we could satisfy phi by assigning y1 to 0 and y2 to 1. And suppose we knew that that was possible, then we would not go on to repairing the f1, the function corresponding to the y1. So what we want is to search for a nicer counterexample. So how do we do such a search? Well, we are going to rely on another advance in symbolic reasoning. These are max set solvers. So this is the solver where you can tell the solver that I want to satisfy a subset of the clauses as much as possible. So in particular, what we tell the solver that, I want to assign x to same as the assignment of sigma of x. But in case of y, I would like it to agree as much as possible with the assignment of y prime. And then you give this max set solver such formulas, and it gives you back a subset of the variables that it couldn't make them equal to sigma y prime. And these will be the variables whose functions we are going to repair. So now we rely on the power of max set solvers. Again, max set is an NP-hard problem, but there is a lot of advance that has happened in the field that we can rely on these solvers. Okay, so how do we go about repairing these functions? So let's say now the counterexample we have is assigns y1 to 0, y2 to 1. So we are going to repair f2. One potential repair for such a function is to say that, well, whenever x1 is 1, x2 is 1, and y1 is 0, we should have y2 to be 1. So we can look at this as a if beta, where beta is a set of literals. Literal is a variable or its negation. Then y2 should take certain value. We would like these repairs to be able to generalize beyond the counterexamples we have. So it would be nice if the repair could generalize to potentially other counterexamples. What does it mean to generalize to other counterexamples? If it could be a subset of, if this beta, which is the set of literals, could be smaller, because the smaller it is, the more it generalizes. But we also want to make sure that it is sound, because all we know so far is that when x1 and x2 are not y1, then y2 should be 1. We don't know immediately that if x1 is 1, then y2 equals to 1 is good. So how do we find such a small beta that is sound? Well, we'll construct yet another formula. And now the formula says that I would like to, we have the formula phi, and I want to say that I would like to have x1 to be 1, x2 to be 1, y1 to be 0, and y2 to be 0. Of course, the solver says you are crazy. You can't have y2 to be 0 even when x1 is 1. So this reasoning that the solver gives us back, it's called unset core. We can use this reason to come up with a sound beta. So what is going on now? We started with a one-level decision list. Now we are doing additional repairs. They look of the form if beta 1, then 1, if beta 2, then 0. And it turns out on closer observation that each of these betas can again be reordered. So we went from one-level decision list to a two-level decision list, which from classical learning theory perspective, we know is can express much more functions in a compact manner. So this is what the repair is really doing. It takes a one-level decision list functions and is able to construct two-level decision lists, while making sure each of these betas are sound. Okay, so let me put together everything. We started with the specification. We generate the data. We come up with the weight functions to generate the data. Then we learn these candidate functions. Then we verify these candidates for which We do a set call. We go on to do repairs based on make set and unset. So there's a lot of advances we are relying on in the field of symbolic reasoning. And finally, we are able to certify that the functions are indeed correct. Since we have been through this for last 40 minutes, the natural question is, well, does all of this work? There's, of course, a new approach, but new approach is what it's solved only if it works. So let's see. We are relying on the standard set of benchmarks. So there are about 600 benchmarks. We compared it with the set of our tools that were designed when we started working on it. These are the tools from very different approaches. So Cadet is based on incremental determination. BFSS is based on abstraction refinement, and C2SYN is based on knowledge representation approach. So first, let me show you how these tools were designed over the period of 5 years. So how much improvement they had been able to attain over the years. Over the set of 600 benchmarks, the improvement over 5 years was from 206 to 280 benchmarks. So of course, this is an area, very active area. There's a lot of work every year. So there was a steady state of improvement, and in 5 years, about 70 benchmarks were improved. The work that I discussed today, we are able to solve 509 instances. In fact, every single benchmark that can be handled by any other app, almost every single benchmark that can be handled by any other approach can be handled by us. So there's a significant increase of 229 benchmarks that we were able to obtain over a period of 3 years. So let me talk a little bit about some of the choices that we made. The first choice was about the samplers. So one question is, how much the quality of the samplers matter? So I'm showing the plots. I should, let me spend a little bit time to decipher this plot for you. This is called a cactus plot in the community. So what does it mean? It says that the corresponding tool could solve 200 benchmarks, each of them in under 1,000 seconds. So ideally, you would want your tool to feature as right as possible on this plot. So what it means here is that the tool could solve 300 instances, each of them in, say, about 400 seconds, and so on. So we are talking about the number of each of the instances that could be solved in under the time here. So now I'll talk about some of the choices that we made along the way. So one of them was that how, we came up with different sampling strategies. So how does the quality of samplers affect the performance? So CryptoMiniSet is a set solver. It doesn't give any guarantees on the samples it is trying to find. Quick Sampler is designed slightly based on the idea that Florian mentioned, so which is on the relaxation. You find an assignment and then you search in the vicinity of that assignment. So if we were to take the Manthan tool and just replace the sampling part, then you see that the performance goes from 509 instances to 332 instances. So a significant decrease if the sampler quality is not good. Another crucial aspect was not doing the repair with respect to the counterexample that we found, and instead trying to look for a nicer counterexample. So typical idea is that you get a counterexample and you immediately go and repair your functions with respect to that counterexample. But we looked for a nicer counterexample. And again, if we were not to do this search for nicer counterexample, the number of instances decreases by another 100. Another crucial aspect was to allow training errors. So if you were to overfit with respect to the samples that we have generated, even though there was no noise, the number of instances we can solve decreases dramatically to 170 log. So with that, let me comment a little bit on some of the interesting future directions. So one is more in the context of formal methods, where we are going from abstraction to approximation. So perhaps this idea has other applications. Coming back to the setting here, we have so far focused on the propositional formula. So these are the Boolean formulas. But of course, not every kind of system specification can be described just using the Boolean formula. So it would be nice to extend it to more richer theories. So there's a lot of work in developing, similar to what the set solvers are. These solvers are called SMT solvers. They can handle more broader theories. So it would be interesting to lift these ideas to much more richer class of constraints. There are also interesting theoretical questions here. In particular, we have a setting where there's an underlying relation. So even the basic questions that what's the ideal distribution to generate the data doesn't follow from the classical learning literature, because IID or uniform samples are, as I showcased, are perhaps not the right answer. And similarly, can we prove some mistake bounds or complexity of learning functions when the underlying specification is a relation? So underlying specification is not a function, but a relation. I also think something that gives a lot of promise is we can use ML techniques for problems where the ML techniques would give us solutions that don't have to be fully correct. It's okay for them to make errors, but they get you somewhere close by. And then we can use formal method techniques to make sure that they are correct by going through this repair and check loop. And finally, are able to certify that the functions that we learn are indeed fully correct. So with that, let me conclude. I talked about our approach Manthan. It relies on advances in constraint sampling, on decision list classifiers and symbolic reasoning. And we are able to solve significantly more benchmarks than what can be handled by the prior set of art. Everything that I talked about today is open source. I would very much welcome for you to try out the tool and see if there are opportunities for collaboration. So with that, I will conclude. I'll be happy to take any questions.
Okay, let's thank Dr. Kuldeep's wonderful talk, and congrats on making such an improvement on this benchmark. Yeah. So let's move on to the Q&A session. So shall I? I think you have a question.
Yeah,
Hello?
Sheila.
Yeah, I'm happy for somebody else. If I've been asking a lot of questions, so if someone else has a question they want to ask, they can go before me, if just in case we run out of time. But if not, I will ask my question.
Yeah, I think you can go ahead.
Okay, great. So just I have two questions related to the experiments. One is that your method is a method that allows for errors. Is that correct? The final solution is an approximation, or does it become it refines to an exact solution?
So the final solution is always exact. So when we terminate with the function.
With a function that is guaranteed to express the full function, the full input. Yeah, okay, great. I'm curious whether of the 509 versus the 280, are you solving the 280 that they were solving as well as others, or are you solving a different class of problem with your technique? Sometimes maybe they're good at solving apples and you're good at solving oranges, and there happen to be 509 oranges and 280 apples, or whether you're solving all the problems that they could solve, which are easy problems, and then going beyond that.
Yeah, so we are indeed able to solve almost every problem that can be solved by any of the other tools. So I think there are about 20 problems out of, if you take not just the 280, but if we take the union of the problems that can be solved by other techniques, we are able to solve almost every single such problem, and then additional problems on top of that.
And do you have a sense of, I'm sure you've done this because of course we always do this. Do you have of the problems that you cannot solve? Do you have a sense of what the obstacle is? Size, compute,
Yeah, so that's an excellent question.
Yeah.
There are many aspects to it. So the first is, of course, this scalability in automated reasoning is always a challenge. So we can handle until, about 5, 6, 7,000 Y variables, but beyond that, it becomes challenging. For some reason that are a bit surprising to me as well. So one of them is right now, of course, this is, after 3 years of improvement. Right now, the step that takes the most amount of time is the learning. Because what we have to do is we have to learn about 5,000 such functions. I mean, we don't learn functions for every bit. We learn for a cluster of bits together. So we have to still learn 1,000 such functions. And that's incredibly slow if you were to rely on any sort of off-the-shelf techniques. And turns out there are no, this looks like a really, problem that's ripe for a lot of advances. So here is the setting. You have a lot of features, a few thousands of features, and you want to learn functions for each of them. And so this is the part that's taking a lot of time, which is why we are timing out on a lot of these cases. The other aspect that's happening is the data generation. So the heuristics that we have are, they work in some of the cases, but what happens is that once you have generated the data, then you will learn functions corresponding to that data. And we do miss out on a lot of very, very simple possible functions. So there was a recent work last year from others in the community that showed that Manthan doesn't always synthesize simple functions. So there are many simpler functions, but we are missing out because the data that we generate doesn't reflect that simpler function. So the data generation part needs to be refined. In particular, what is happening is that we are learning. So the real weakness of the method right now is that the initial candidates that we learn are only based on the data. We are not able to take advantage of what the function, what those constraints are, or rely on those constraints, even to guide the search for these functions and so on, which is what a lot of other techniques were able to do, when they relied on abstractions and so on. So we are not using perhaps some advantage that one can have by looking at the functions here. So I would say these are the two major bottlenecks. I mean, there are other aspects of it, but really, if we are not able to solve the benchmark, what happens is that the functions that we generate, you can see on the decision tree, if you look at the entropy at the leaves, you see that we haven't really generated a good candidate. So no matter how long you go on to repair it, the starting point is so far off that there's little hope in being able to generate the correct functions. And the part about the learning becomes even more crucial. What you asked earlier is the order of the variables that we have here. Because if you consider, how people really design systems, they are always designed in a modular manner. So you have a big system, but all the components are usually small components that you put together. Just from the data, we are not able to figure out that structure. So it would be nice if we could somehow use the formula and then guess the structure and combine the learning. So that's why we are not learning good candidate functions for the cases we are not able to handle.
Excellent answer. Thank you so much. It's really fascinating. Thank you.
Yeah, I mean.
Yeah, so just building off of what you said about the most time-consuming part, and maybe I'm misremembering, so please correct me, but I think you said that somewhere the functions that are learned, it's okay if they're not perfect because then they go through the verification process and all that. So a totally non-concrete idea, but something I'm curious about is whether current sequence generation models can be used to actually generate potential functions that would represent either the tree form that we see here or the reduced list that you pointed to afterwards. I mean, if we're talking about approximations that will be verified later, and if we also have access to a data generation process that could potentially generate an infinitely many number of, training points with the corresponding trees that, are then learned, even if they are time consuming, we then have a data set that can be used to train a sequence model, and then we could get maybe initial candidates for those models. Is that something you've thought about, or do you think that's impractical?
Well, no, I mean, this we have thought about that there might be a possibility, but we haven't really looked into. I think that if one can pull off this approach, it can have a significant impact. So, yeah, I mean, what you are suggesting, can we use sequence-based learning methods? Perhaps yes. I mean, there's no reason to say no here. It's just that can we pull this off, all of this? So we have tried some ideas, trying to give the entire formula to LLM kind of setting. Those cases, the candidates it comes up with are not, because these formulas are very, very large. So, we are talking about few tens of thousands of lines of constraints. So it's not immediately clear how to go about it.
Yeah.
But just because we couldn't pull it off doesn't mean that. Yeah, I definitely think, but it's also limited expertise on our end. So.
Right, and one potential challenge that probably immediately comes up is that the problem of the data generation that you talked about would be further exacerbated because the models are probably going to overfit to that, and that might mean you're missing out on parts of the search space, where search space here means the discovered functions afterwards. So,
yes, I mean that's of course a challenge. Sampling. Finding a satisfying assignment itself is an NP-complete problem, NP-hard problem. Generating samples according to a distribution is much, much harder problem. So we had to be cognizant of, putting everything together. So right now that's also one of the reasons why we are relying on decision trees or things that don't require humongous data, because we are able to generate few thousands of samples. But, at the same time, when one is really trying to solve these problems, it's okay to parallelize the process of data generation, and you could generate many more points possible. So I definitely think it would be interesting to use more sophisticated learning techniques.
Cool. Thanks very much.
And as you mentioned earlier, yes, the one aspect is the learning method doesn't have to get these functions fully correct. In fact, we also tried to see, and there was an approach in the past that tried to solely rely on the learning to get these functions to be fully correct. And that sort of doesn't work out, because no matter how much data you generate, getting the functions to be exactly correct is just very, very hard. So it's much better that you get somewhere close by and then you go on to repair it.
Sounds good. Is there any more questions from the audience? Yeah, if no, we can call an end to this talk. Thank you again for the wonderful talk, and hope to see you in person in Toronto.
Yeah. All right. Thank you.
See you.
Thank you.
Yeah. Bye.